for the first video in this new chapter. So if you got the hang of SN2 reaction, I think it might be a little bit easier to think about these other reactions, SN1, E1, and E2 reactions. And the most important thing, though, in this chapter is going to be how those things actually compete with each other. So one thing it's good for you to know, if you're going to be a good chemist, is that the chemicals don't know what you want them to do. Okay, so they're going to do whatever that physically makes sense to them, chemically makes sense to them. And so even if you try to set it up for, like, say, SN2 reaction, it might end up being an E2 or SN1 reaction or something like that. So there's going to be sort of competition between these four different reaction pathways when you have a leaving group containing substrate. And so for that reason, this is kind of the goal, and that's what we're going to build up towards in the first few videos in this chapter. Okay, first we want to introduce you to the SN1 reaction, and if you remember what SN2 stood for, that was nucleophilic substitution by molecular, and the 2 stood for how in the rate determining step there were 2 molecules involved, right? That's not to say that there's 2 molecules involved in the reaction. There's 2 molecules involved in the rate determining step. And so maybe that's the first emphasis here, is when we say nucleophilic substitution unimolecular for the SN1 reaction, one refers to how there's only one molecule, unimolecular, in the rate determining step. I think I'm gonna have to sneeze. Maybe not. And then, so here's a one example of an SN1 reaction. Often it's also referred to as solvolysis. It's almost synonymous with SN1. And the reason for that is often the solvent liquid that you're using to dissolve your substrate is the one that tends to end up being the nucleophile that substitutes. And so for that reason, it seems as though the solvent molecule did the lysis, as in broke up the carbon leaving group bond and then inserted itself. That's lysis, means breakup, right? So it's often also referred to as solvolysis, and that's something I definitely want you to be aware. Another thing I want you to notice in this reaction, unlike maybe the SN2 reaction, is that water, of course, is what do you remember what kind of nucleophile? It's a fairly poor nucleophile, and yet this works. And the other thing I want you to notice is that the substrate is too bulky. For SN2, remember that's a tertiary halide, right? And that's too bulky because nucleophile needs to be able to attack this carbon, and yet it's tetrahedral, like there's something pointing at every direction. There's no way to for the nucleophile to reach this without bumping into one of these hydrogens of the methyl groups and such. So it's just too bulky. Okay, so when SN2 reaction happens, SN1 reaction indeed does happen. Here's the experimental observation that you can make. And this is the reason why we know the mechanism is SN1 mechanism, as we'll see. Okay, and the one thing you can observe is how fast the reaction takes place. The kinetics, or the reaction rate, is dependent on some constant times the concentration of the leaving group substrate, but not any nucleophilic compound. It's just depends on just this one compound. The rate does. So it's a first order reaction. Okay, what does that mean? That means that in this case the nucleophile that's substituting is water, but water is not involved in the rate determining step, right? Remember, when we say first order, that means there's only one molecule involved in the slowest or the rate determining step of the mechanism of the reaction, right? So that's what gives us the insight for the mechanism we're going to look at in a sec. Excuse me. So let's think about this. So because it's first order and it really just depends on this molecule, so the hardest part of the reaction must be happening all by itself, like this. The leaving group leaving. How do I know that? Well, first, it cannot be that the nucleophile adds to this first and then the leaving group leaves or something like that, because you cannot accommodate more than 8 electrons. And since we know that this molecule is definitely involved in the rate determining step, and the hardest thing that this has to go through is the dissociation reaction. Right, which will get us to the carbocation, which is very unstable, right? It's a high energy species. Because it doesn't meet the octet. So you have to go from low energy to high energy, so that would be a very slow reaction or mechanism step with a pretty high activation energy. Okay. Now that if that happens, I want you to notice how electrophilic this is. And so for that reason, it's very electrophilic. Even a poor nucleophile like water, that all of this is dissolved in. Remember, this is a poor nucleophile. But the one thing that's going for it is it's very abundant. How do I know that? Well, it's because it's the solvent. Oftentimes in the reaction equation like this, here's a reaction equation, solvent is often written around on or around the arrow, but that's not a strict rule, but that's the common convention. I just want you to know. Because this carbocation is so electrophilic, even a poor nucleophile would be motivated to attack it. It's kind of like if you dangle something that's really, really yummy looking, even a not so hungry person might want to go for it. It's kind of a similar analogy there. And what that does is you would get to this intermediate. Maybe move this over. Right, and now there's some sort of an activation energy involved in this step as well. And to get to the product from here, I want you to notice that's the product. We just need to lose a proton. So we could be sure that something is acting as a base. Now there's two choices here. Bromide is negatively charged, so it could act as a base. Or remember, the most abundant species is the solvent, the water molecule. And so for that, because remember, solvent is the major component of your solution. Those are both candidates, and if you compare the basicity of these two species, remember bromide is the conjugate base of hydrobromic acid HBr, which is a very strong acid, which means that the conjugate base is not basic at all. The reverse reaction doesn't happen much. And so for that reason, water actually is the most basic species in this mixture, even though it's not very basic compared to, bromide. It's more basic. So maybe we'll say okay. So that gets us to the product, as we said. Okay. So now let's think about the reaction coordinate energy diagram. Okay, just to summarize everything that we just saw here, and then in this last step there might be some activation energy involved. So here's the energy axis, and here's the reaction coordinate. Remember, reaction coordinate just means towards the left, that's when the reaction just started. Towards the end, to the right, that's when the reaction ends, or the product, right? And in between you have the intermediate. So the x-axis just tells you how far you've gone through the reaction pathway. And maybe we'll say here's the substrate, and the product is maybe slightly above or lower in energy than the substrate. It's really actually hard to tell. It's about the same energy level. Now, what we could be pretty sure of is that the carbocation intermediate is very high in energy, and then this species, it's the same as this structure, it should be lower, much lower in energy. Why? Because at least it has a positive charge, but at least all the atoms meet the octet. Okay, so here, this must be like a rough, maybe this is a little lower, reaction energy coordinates, and I guess you get to see my screen habit, to go from here to here, the species must have had to go through like a reaction pathway like this. Remember, this is energy. And then from here to here, something like that, and then something like that. Okay, what does that tell us? Well, that tells us that the first activation energy is pretty big, whereas the second activation energy is not that big, and neither is the third. I can't really tell you the exact values, but relatively speaking, this should be the largest for sure, right? What does that tell us? Well, that tells us that that step must be the rate determining step, because that's the hardest activation energy that this compound has to overcome. Okay, so, and the question of course is, does that make sense with the actual observed phenomena? And yes, it does. It should only depend on this compound, and it does. In this step, the nucleophile or anything else, nothing else is involved. So in the next video, we'll think about the carbocation intermediate in more detail. Okay.